Welcome to the short discussion on the temperature stresses in axially loaded bars. This is also one of the last topic in the stresses and strains chapter in strength of materials 1 course. So I'm hoping that by the end of this particular discussion, the learners will be able to calculate the stresses developed in the materials that are exposed to the temperature. Also able to calculate the stresses in the composite materials or composite sections which are exposed to the temperature changes. So let us look at the general phenomena that we can observe anywhere. So let's say there is a beam, simply supported beam, and we know that the simply supported beam, one end is fixed, another one is having a pin or roller support. Of course, in this case, there is both sides rollers are there, and if there is a rise in the temperature, what possibly can happen is the member will try to expand. So when there is an expansion here, in such a situation, we know that because whatever expansion happen, that will be freely expanded. The material freely expands. As a result, no stress will develop or no strain, because there is no stress. There is no strain developed, no stress developed. But on the other hand, when you try to restrain the members at their ends, such as this, now here we are putting a clamp or fixed support. The other side, other case, we have left it freely. So when you try to fix it, what happens? When the temperature is raised or even fallen, at that case, what happens is the material, suppose temperature raised, the material wants to expand. When the material wants to expand, the supports will not allow it to expand. Therefore, what happens? The supports actually push in the entire bar, so the member is subjected to compression. In that way, the compressive stress develops here. There will be some amount of strain, and right, in the process, it will push it down. So some strain in the member, and then accordingly, the internal phenomena, there will be some stress develops. Right? So here the concept of here the composite sections also similar to this, right? Because the members are fixed at either one end or both ends. Obviously, there will be a development of stress and strains in those members. Remember, when it is freely supported such as this, the material allowed to be expanded, there is no problem of stress. There is no question of development of stress. Right? So with that basic understanding, let's look at this the concept of stress development due to temperature changes. So normally what happens is ordinary materials, if you take any material generally, right? When the temperature is raised, the material try to expand. When the temperature is fallen or cooled, when the member is cooled, it will try to contract, right? So this is the 95 or 99%. This is the situation, but there are some materials, right, which are not following this rule. They may not be expanding all the time. There are we used to hear that some of the ceramic metals, right, they are acting in a kind of uh, 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 kind of behavior that is totally different from the normal materials. That means when the temperature is raised, they can contract and so on, right? Except we are not talking about those materials here. We are talking about the normal or ordinary materials in this particular context. So if there is a member which is fixed at one side and even other end is of course free here, even in that case, because when the temperature is raised, for example, when the temperature is raised or contracted, although this member cannot expand here, but here it can expand, and thereby the stress what is supposed to develop will be lost. So in other words, it expands freely, and when the temperature is decreased, again it comes to the normal. So the temperature stresses, once they are once the temperature will the action will be taken back. So if here the observation that we can make is, unless there is a restrainment, there is no development of stress. So however, free expansion of some material is prevented by some external force, then the stress set up in the material. So that's the point which I just now highlighted, right? So now let us look at into the some mathematical background of the stress strain development in the bars exposed to the temperature. Let's say there is a bar which is fixed at one end and the free end at another end, and the bar is having a length of L. Obviously, when there is a temperature rise or fall, the length of the member get affected. The length of the member can be either increased or it can be decreased depending upon the temperature change. Right? So if this, we have studied this in the 10 plus 2 in the chapter called heat. Right? There we have studied when there is a change in the temperature, the length of a member will change by an amount, say delta L, and that delta L, right? So that delta L, and if the change in the member, that what you call length of the member is delta L, and if the thermal coefficient of thermal expansion, every material is having some kind of coefficient of thermal expansion, which may be different from the other materials, right? So that coefficient of linear or thermal expansion of the material is say alpha, right? So the change in the length is taken as L alpha T, right? That delta L, what we are saying, that can be equivalent to L times alpha times T. In other words, it is proportional to the temperature and proportional to the alpha value. More the alpha value, more the expansion. Right? So once you got this change in the length, now you will be able to calculate the strain. So basic, the fundamental understanding is that because of the temperature change, there is a change in the length of the member, which is equal to L alpha T. Right? So this is from the very beginning we have learned that. So now once you got the deformation or change in the length, you can easily calculate strain, because strain definition is no change in the length by original length. So change in the length is L alpha T divided by the original length is L. Now you got the strain. So always once you got strain, because most of the stresses that we are taking as within the elastic limit, so follows the Fick's law. Therefore, it is simply multiplied with Young's modulus, will be getting the stress. Right? So stress is alpha times E, because alpha T is strain. You simply multiply with the Young's modulus, you will get the stress of that particular material. Now the composite bar, compound bars are constructed from different materials or is it together, right? So in those cases, let's say different materials we can take, either aluminum and steel or steel and brass, different materials we can take. So in all those cases, the strain development can be worked out using this, right, alpha T, right? Here what we just now told, alpha times if delta T is the change in the temperature. Here T is taken as a temperature change, so we can even write it as delta T. And this particular one is simply generalized Hooke's law, right? 1 by E times the strain in stress in that direction, and to mu Poisson's ratio times the stress in the other two directions, because this is a longitudinal strain, the other two are the lateral strains, right? So this is how we can calculate the strains in for a three-dimensional state of stress. When there is a rise in temperature or change in the temperature, the way we can calculate the strain. Once you know the strain, of course, you can calculate the stress easily. So let's look at the composite bar situation. So here we just discussed in the previous session about the composite bars, where the composite bars are supposed to have these conditions. They must have a same length, and they must be made up of different materials, or they must be having different modulus of elasticity, right? Or different materials made up of, and they must be clamped or fixed, right? And so that they can be acting as a single unit. So all these conditions are satisfied, then we will say there is a compound bar. Here is such a compound bar made up of brass and steel, right? So if you look at this particular bar, when there is a rise in the temperature, this is the original bar before when there is no change in the temperature. Once the temperature rises, the expansion of the material takes place freely, right? So when the material is, of course, this is in the free state. Is free state. It is, it's going to be expanding like this. So it is expanding here. No, it is also here. It is also clamped, right? Here also it cannot come out here. They will be acting together, because that's the definition of the compound bond. So now, if you look at in a free state, what's going to happen is, suppose you are not restrained here, then what happens is they will expand. So that expansion may not be uniform, because brass having a different thermal expansion coefficient. Although length is similar, right, and temperature is the same for both, but the alpha, because of more alpha value, this brass goes supposed to be, when in the free state, it's supposed to be expand more, whereas steel is a little bit less. Right? But because they are being restrained, they are made it in such a way that they are supposed to act together, then the final expansion of that is going to be equal, right? So in the process, what's happening is, the brass, which is originally supposed to be uh, expand more, it has been pushed inward, right? So whereas steel, which is supposed to be expanding up to here, it was being further pulled down, right? That means the conclusion that we can make here is, if the value of alpha, which out of the two metals, let's say here two metals we have considered, among the two metals, whichever metal is having more thermal expansion, that is finally, because it is made it as a single unit, finally that particular member is pushed inward, right? And when it is pushed inward, it's going to be in combustion. Whereas the metal which is having less thermal coefficient of expansion, that is to be in a tension, right? And here, so from that we can write one condition, that the tension in one of the metal is equal to tension in the compression in the other metal, right? So that's the one of the fundamental equation in this concept. Tensile force in the steel is equal to compressive force in brass. Here, why steel is in tension? If you look at the thermal coefficient of expansion of the steel is less than that of the brass. Brass having a more thermal coefficient of expansion. So therefore, brass is push in. Therefore, that will develop the compressive force, whereas the steel member has been pulled out beyond its free expansion. Therefore, it is subjected to tensile force. So from there, we can get a formulation here. Tensile force in the steel as stress times its cross-section area, whereas compressive force in the brass is nothing but the stress in that particular brass into the cross-section area. So either here you can represent either with sigma symbol, or you can, it doesn't make the but remember, stress times the area. Now the other equation we can generate here is because the actual expansion in the steel is equal to actual expansion. Ultimately, both are subjected to same amount of expansion, right? But actually, what is happening is one of the its actual expansion in steel is equal to actual expansion in brass. So, what is the actual expansion in the steel? Steel is no, it is subjected to tension just now we discussed, and the other one is subjected to compression. So L alpha T is the expansion caused due to the temperature. The other one is this was the tensile force imparted by the brass on the steel because brass is expanding more. So during its expansion, it takes away the steel. Therefore, there is a tension develops steel. And the other end, the actual what actually is supposed to be more, it should be in tension if it is freely expanded. But what's happening because it's acting together, and steel cannot go beyond that. And they are supposed to act together. Therefore, in the process, what happening is the brass is pushed forward. Right? So that's why here the compression develops. So finally, that expression here, actual expansion is due to temperature alpha, both sides you can tell alpha T, right? But because it is in which one? The steel is in tension, we will write it as the stress developed due to the tensile stress will be developed. So plus the stress, what do you call expansion formula. What is expansion formula? We know delta is equal to PL by A, right? Delta is equal to PL by A. Delta equal to PL by A. Right. So P by A we can write it as stress. So it is sigma L by E. Sigma L by E. That's what it is. So this is the tensile stress developed in the steel, right? And this is the compression, therefore negative alpha sigma by E times. So we can rearrange the terms even, right? We can bring this to this side. So you'll be getting this kind of formation. So now using this particular formation, we'll try to look at one simple example to have a better understanding. So there is a flat steel bar 20 mm by 80 and 8 mm that is placed in between the aluminum Li bars of 20 by 60 mm each. So there is a steel inserted in between to the between aluminum. Right? So aluminum here is having this cross thickness of 6 mm and steel is having the thickness of 8 mm. Of course, the length, because it is a composite one, the length is same for both. So this is the arrangement. Now the three bars are fastened together. So they, because they have to act as a single unit, they have to be fixed at both ends. So it happened at a temperature of 75 degrees Fahrenheit. Of course, it doesn't matter it is centigrade or Fahrenheit. After all, we require the change in the temperature. Right? Find the stress in each when the temperature of the whole assembly is rising to 120. So if the temperature was raised, so by around 50 degrees Fahrenheit, then in that case we are supposed to do stresses. So the straightforward, let us look at the three steps we will try to get it solved, right? So as a simple step, first of all, we should know what is supposed to be found and what are the given things. Our task is very simple. We have to find the stresses in aluminum and stresses in steel. That is sigma A and sigma S. We have two equations and two unknowns with us. What are the two equations? One equation is sigma S AS, that is tensile force or tension in steel is equal to compression in the aluminum. Sorry, what is this? Yeah, aluminum. Sigma A very small matter. So this is one equation. The other equation is right, L alpha T. What is that? just now I discussed, right? Temperature change due to that um, the expansion due to the temperature. So what is the expansion due to LR40? Right? So LR40 of alpha S LS alpha suffix S alpha S LS L140. It is the temperature change which is here of course. Um, Plus is our equation plus if the tensile stress plus tensile stress. Tensile stress is simply sigma by uh, sigma L, that is sigma S LS by this must be equal to alpha CLC T as D is the T or delta T because the change is a change in temperature, remember that. And this side is a compression. So this is in compression. So alpha sigma C LC by EC. So this equation is sufficient. Two equations unknowns, all the values, rest of the things are except these are the two unknowns. These are. So let's look at the solution. First apply the equation total tension is still equal to total compression. Here Fs, Fa is used, it doesn't matter if it is sigma S or even sigma A. Okay, anyway it's we can represent it any sigma. So that is Fs or sigma S is equal to simply you get Fa. So you get a relationship between sigma S and sigma A or Fs and Fa, right, based on the simply areas. Right here, the areas of this aluminum is what is that? 20 times 6, 120, but again 120, so 240, 240, and this one is 160. So 240 by 160 is approximately 1.5, right? So that's you got a 1.5 times the aluminum stress. Now use the second condition. The second condition says this one, right? The actual expansion is still equal to actual expansion. So based on that, we have all the values in this. Alpha is 6.4 times 10 to the power minus 6, and T is the temperature change, and 20 mm is the length of the particular member, and the other side here itself, we got just now this relationship 1.5 times Fa or sigma A by its length modulus into the length. Actually, length can be cancelled out throughout because all the lengths are same. And 12.8 mm, this is twice that value. So 12.8 times 10 to the power minus 6 times T minus Fa by 0.7 times 10 to the power 5 lengths, what you call lengths modulus of the last side. So simplification leads to because the entire equation has been converted in terms of stress of all alumina, so you get that value. So you got this from the relationship 1.5 times that. So this is how we can solve the problems of composite bars subjected to temperature.